We'll take a look at number 68 here. The handbook lists the solubility of calcium monohydrogen phosphate as 0.32 grams of calcium monohydrogen phosphate dihydrate per liter, and lists KSP as 1 times 10 to the negative 7. Are these data consistent? That is, are the molar solubilities the same when derived in 2 different ways? They're supposed to be. They're supposed to be the same. And so let's take a look at the molar solubility here. And so this first one, 0.32 grams of calcium monohydrogen phosphate dihydrate per liter. Where did this come from? This is empirical. This is just from experiment. And so somebody took a liter and determined how much dissolved in that, and they got 0.32 grams to dissolve. And so this is just, if it's been reproduced, this is just experimental fact. And then we need the molar mass of calcium monohydrogen phosphate dihydrate. So I don't want to calculate the molar mass, so I'll just look it up here. And that's CaHPO4 dot H2O, 2H2O. All right, this is what we call the anhydrous form. Anhydrous has no water, it's 136. And then if we have the dihydrate, we have to add 2 times 18, 36 grams per mole extra. So 172.09 grams per mole. Will give us moles per liter, the molarity. So that's what we want. Go ahead and calculate that. .32 divided by 172. I don't know. This is going to be 0.00185. 949 molar. We're allowed 2 sig figs, so we get 0.0019 molar. And let's take a look at the next one here. All right, the solubility from the KSP from KSP. We're going to get calcium monohydrogen phosphate solid that splits up into calcium ions and monohydrogen phosphate ions. So we'll have KSP, which is equal to 1 times 10 to the minus 7. And this is going to split up into S and S. So we'll have plus S, plus S. So at equilibrium, we'll have S molar and S molar. Right? And so this will give us S squared. So the solubility is just the square root of this. So the square root of 1 times 10 to the minus 7. .0000316 2 molar. Only allowed 1 sig fig there, so I'm just going to go to 0.0003 molar. Okay. Are these data consistent? No, they're not consistent. If there's a discrepancy, how do you account for it? I mean, they're quite a bit different. This is 0.002, this is 0.003. There's a huge difference between these two. And so how would we account for the difference? This solubility that we calculated here, based on the KSP, KSP is determined by the calcium, the free calcium, and the free monohydrogen phosphate concentration. But if we look, the actual solubility is like 10 times bigger. Do you see that? Almost 10 times bigger, the actual solubility. And so what that means is that there could be more species dissolved in here. That is, in addition to the free calcium, we might have calciums that are paired. Like this. We could have calciums that are paired like this. And due to these ion pairing interactions, we get more calcium than what we predict based on the KSP. The KSP is going to be measuring the free calcium and the free monohydrogen phosphate. And so due to having these other species present here, the actual solubility is greater than what we might think based on just the free ions. And the free ions are what we use to predict KSP. They're coming equal to the free calcium ion plus the free monohydrogen phosphate. And if you have ion pairs like this, then the actual solubility is going to be higher due to that. This goes back to the beginning of the chapter, actually chapter 18. And there's a section here called Limitations of the KSP Concept. So for example, if we're calculating the solubility based on lead and iodide, the free lead ion and the free iodide, then that's just, oh, this is common ion as well. And we have something like this. But what can happen is that the lead, in this case, the solubility was equal to the lead concentration, can exist in other forms. This one was particularly involved. And so the KSP-based solubility is just based on the free lead and the free iron. But if you have an ion pair, this is going to be an ion pair here. You know, there are more possibilities for ion pairs in this particular one than that one because of the charge. So we have this as an ion pair. This is an ion pair which forms into a neutral pair or grouping. This isn't actually a bond. This isn't actually a molecule. These are just two iodides that are kind of stuck onto the lead. You know, it's a molecule-like ion pair. And what that means is that there's actually more lead dissolved than we think, because if we're just measuring this, then we aren't getting all the lead. You know, because there's this, and in addition, if we have excess iodide, we have these two as well. So the solubility calculated based on KSP is just using the black concentrations here. But the actual solubility is the black concentrations plus the blue concentrations to give us the total concentration of lead in there. And when we do it by seeing how much dissolves, we're getting the total concentration, because if you start off with this and see how much dissolves, then it's going to, some of it's going to dissolve to form this, and that. You know, but when we do the KSP, we're only measuring this because that's what we're trying to analyze for. So that's what the discrepancy arises from. It arises from ion-pairing type interactions that can occur. What was the next question?
number 71. And so for the exam, would we expect to see problems more so like the one that you gave us with quiz?
Well, the conceptual might be something like this. I think on that exam, on the old exam, there was a conceptual problem.
Is there a video on Canvas with you going over the old exam?
What's that?
Is there a video on Canvas with you going over the old
Yeah.
exam?
It's Saturday. I forgot to post let me check if I posted the link or not. Okay, let me Thursday and Saturday. Okay. Let me make sure if it's check the link.
Do you know what the dates for them?
It should have been on. It was Thursday and Saturday, the 14th, 12th, and the 14th. Let me make sure I did that because maybe I forgot to post a link. So I'll do that today. Check it today after class. It could be, the questions could be similar to the questions on the. Did you go through it again, the practice or the old exam? Were there any questions from any of the problems there?
Well, are we going to have the charts?
Yes.
Okay. Because I feel like a lot of them we need to look at the charts.
Yeah, you do. Let me try to send that to my mail here.
I think I'm pretty good when it comes to like the more, I guess like the less involved problems when you're asking for like the KSP of something. You just got to do like one ice table and do like the KSP and stuff like that. That's just a lot of things.
Mm-hmm.
Some of the other things are really like two steps. I guess I get confused when I try to explain the problem to myself because I don't understand.
Okay.
Like for, actually, can we do 29 instead of 79?
Okay.
I feel like that might be something else on the
All right. What is the minimum pH at which cadmium hydroxide will precipitate from a solution that is 0.005 molar in cadmium 2+? So, well, before I forget, on the 512 and the 514 exam would be the old exam 18. So check for those after class. For this one, cadmium hydroxide will precipitate from a solution that is 0.055 molar cadmium 2+. So whenever we're doing precipitation or dissolution, we always write the KSP equation for both. And so what we're going to do here is we want to saturate the solution. So sometimes it's confusing because, where do we put the 0.086 molar chromium 3 plus. And the 0.086 molar, we don't want any of that to precipitate, so that has to remain at equilibrium.
I think you're looking at number 30.
Oops. 0.055. 0.055 molar cadmium 2 plus. And so this has to remain in solution, 0.055 molar. We don't want anything to happen to that. And so that's it. And so what we're trying to figure out is what must be the equilibrium hydroxide. What is the max we can have here? Because if we had 0, then yeah, it can stay. There's going to be no precipitation. But as we start increasing the hydroxide concentration, we run the risk of precipitating out the cadmium 2 plus. So what is the max? Well, the max, whenever we're dealing with precipitation or whatever else, is going to be equal to the KSP. KSP is going to be for saturated solution. So this is going to be cadmium 2 plus times the hydroxide squared. Yeah. And so for the cadmium 2 plus, we want it at 0.055 molar, and then we got to figure out what is the hydroxide. Because if we have this equal, that's going to be saturated. If we exceed this, then it's going to be supersaturated.
Point 0055.
Okay, 0.0055. It'll be supersaturated. Okay, so we just calculate the hydroxide here. The hydroxide concentration is going to equal KSP divided by 0.0055, and we'll take the square root of that. This is going to be the max hydroxide. If we exceed that, we'll get precipitation. Okay, once we calculate the hydroxide here, then we'll calculate the POH, which will be the negative log of that hydroxide. So as the hydroxide increases, the POH decreases. And then we'll figure out the pH in this. And so what do they say? What is the minimum pH which will precipitate in the solution? What is the minimum pH at which it will precipitate from the solution? Well, one of the confusing parts of this is this. If this is the max hydroxide, then this is the min POH. Because the smaller the POH gets, the bigger the hydroxide gets. And so this is the min POH that we can have. We can't get smaller than this POH. If we go smaller than this POH, then the hydroxide grows bigger and it precipitates. And so there's a problem with the phrasing here. Maybe I didn't notice this earlier. Maybe I did. It shouldn't say minimum, it should say maximum. Because if we're dealing with a minimum pH, then this could be the maximum pH. So we can start off at a low pH. Low pH means very low hydroxide. As we increase the pH higher and higher, we get more and more hydroxide because we get less and less hydronium. And so it should have said, what is the maximum pH that we can't exceed? Because if we go above this pH, then we're going to get precipitation. Low pH is no problem. We're not going to get any precipitation because low pHs are acidic. This is base. And so the max pH will be whatever that is. And this would be the max. We can't go above this pH because if we go above this pH, we have too much hydroxide. It's going to precipitate out. And so we just plug in the numbers here. We have to find the KSP in the book, Appendix D, and then plug it in. Is that all right?
Yeah.
This is the setup. We could calculate it. And it depends on the KSP. Sometimes it's so little hydroxide, it's actually acidic. That is, it's weird to think about. You could have hydroxide precipitates that occur in acidic solution. That is an acid solution that's dominated by hydronium. So how can you get a hydroxide precipitate? Well, the hydroxides are so insoluble. And so, for example, iron 3 hydroxide precipitates at like a pH of 2. That's the max pH. That is, pH is under 2, we get no iron 3 hydroxide. pH is above 2, we get iron 3 hydroxide precipitating because it just takes a minuscule amount of hydroxide to precipitate it because the KSP is so. Actually, do I have my KSP here? Because the KSP is so small.
2.5 times 10 to the negative 14.
400 hydroxide?
Oh, no, this is for.
For this one?
Yeah.
Okay, it's not. 2.5 times 10 to the negative 13?
14.
14. Well, it's pretty small. Not as small as iron 3 hydroxide. So we could just go ahead and do this calculation. 2.5 times 10 to the minus 13. And then divided by 0.0055 equals, and then take the square root of that. And so the hydroxide concentration I get is 6.74 times 10 to the minus 6. Is that what you got?
Yeah.
Times 10 to the minus 6.
Wait. No.
No.
I got 2.13 times 10 to the negative 6.
2.13 times 10 to the negative 6. Let's see.
Before you square root it, you should get like 4.545 times 10 to the negative 12.
All right. Yeah, I don't know. Something's weird about my calculator sometimes. You got 2.13?
What was that?
Did somebody else get 2.13 too?
For
For the,
before square root.
no, after you square root.
I got 6.7. Times 10 to the negative.
Let's do that 2.13.
So I think 2.13 times 10 to the negative 13. Divided by 0.00. No, wait.
Yeah.
I'm sorry, it's 2.
Times 10 to the negative 14.
14?
Yeah.
Not 13.
No,
No, it's 2.132 times 10 to the negative 6.
The KSP is 2.5 times 10 to the negative 14.
And I'm not doing that.
He passed it.
What was KSP again?
It's 2.5 times 10 to the negative 14. Yeah.
No.
Yeah.
Okay, do you guys get it?
Yeah.
All right, then. Because now I got 9.5 times 10 to the minus 7. So I don't know. It's so weird. I can't understand. I can miscalculate it. on this. All right, so what is the pOH for that?
I got 5.67,
Okay, 5.67, which means the pH is
8.33.
8.33. So any pH lower than this, we don't have enough hydroxide. So we need not only it to be basic, but we need it to be quite basic. It has to be greater than 8.33 to get enough hydroxide. And so this is the max pH that we can have before precipitation. Any pH above this will precipitate. Now take a look at the KSP for hydroxide. Look at that. 10 to the negative 38. At 10 to the negative 38, this barely requires any hydroxide. And therefore, you can have a very acidic solution. So the max pH for iron-free hydroxide is like 2 something, or even in the 1 range. That means at a pH of 2, there's already too much hydroxide present, even though that's strongly acidic. So where does the hydroxide come from in a strongly acidic solution? It comes from Kw, water molecules colliding. You can't stop that. So when thinking about hydroxide precipitates, you always think about the maximum pH that we can have before it starts to precipitate, because the higher the pH, the more hydroxide. Okay, other questions? Yeah. What was the other problem, 71 you were asking about?
Yeah. Let's do 33. 33 is better.
33? All right, 33. Determine whether 1.50 grams of oxalic acid can be dissolved in 0.200 liters of 0.150 molar calcium chloride without the formation of calcium oxalate precipitate. So we're dealing with multiple equilibria here, because we have the KSP equilibria. So we have the KSP equilibria, which is going to be calcium oxalate, solid, goes to calcium ions plus oxalate. And then we have the Ka, equilibrium for oxalic acid, which is K1 and K2.
So for these types of problems, should we always just start out by writing the KSP?
Yeah.
Okay. I think that's like one of the main problems, figuring out where to start at.
But, the thing about this chapter is we do things differently depending on what the question's asking for. So sometimes we'll do this. Like, if somebody's given KSP and Ka, the tendency is just to automatically combine them into a KSPA equation. And so I would think, okay, we're going to combine this into KSPA because we've talked about KSPA before. But sometimes we don't do that. Sometimes you need to do that. Otherwise you can't solve the problem unless you do it simultaneously. Other times we don't do that. This is a question of, will something precipitate? And so when we have something, will something precipitate, then, what we need to know is what the QSP is, KSP versus QSP. We need to make sure that if we don't want to precipitate, then QSP should be less or equal to KSP. But in this case, they give us how much calcium we have. We have 0.200 liters or 200 milliliters of 0.150 molar of calcium chloride. And so 0.200 liters of 0.150 calcium chloride, which means that this is going to be the calcium ion concentration. Because for every calcium chloride, we have more calcium. And so this is the same type of deal. We don't want it to precipitate like that last problem. We don't want this calcium to precipitate. We want this calcium to remain here at equilibrium, 0.150 molar, shouldn't precipitate. Now, they're going to make our life a bit easier. The reason they're going to make our life a bit easier is because we're not adding a solution of oxalic acid. If we were adding a solution of oxalic acid, then we'd have to do solution dilution. But we're just adding grams of oxalic acid, and we're going to assume that those grams of oxalic acid do not change the volume significantly. And so we're going to add a 1.5 grams of oxalic acid to this, and then C. So how many moles is that? And so we need to calculate the molarity of the oxalic acid here. Okay, oxalic acid is easy to calculate the molar mass. So hydrogen's 202, 2 carbons is 2402, and 4 oxygens 6400. It's 4, 0, 6, 10, 90, 90.04. And so the molarity of this is going to be 1.50 grams of oxalic acid, oxac for short. 1 mole of this weighs 90.04 grams, divided by how many liters. So we're assuming the volume didn't change, so it's going to still be 200 liters, 0.200 liters. And this will give us the molarity of oxalic acid. Can you tell me what you get for this one? Smaller. Okay. Now, what QSP is given initials. So we're going to keep this at 0.150 molar here. What we need to figure out is what is the initial concentration of oxalate? And then we can calculate QSP. You know, is this going to shift right? Is it going to shift left? Or is it going to stay at equilibrium? We don't want it to change because we want it to be the same or not. And so this cannot.
I don't get that.
You don't get this part? Okay.
No, for the,
You don't get this number?
yeah,
Okay. What did you get?
8.3296 times 10 to the negative 2. So 0.083296.
0.089.
Okay, 0.083296.
Yeah.
83296. All right, so 2 people got this? All right, then we'll go with that.
I think I look at the grams.
Okay.
Okay. So whenever they're asking, will something precipitate or won't it, then we have to ask ourselves the QSP, you know, what are the concentrations here? So this problem is more complicated because this is oxalic acid. In order for precipitation, we need free oxalate ion. You know, we can't have oxalic acid, although it could happen, you know, but we want to know what the free oxalate ion is. And so in order to determine what the free oxalate ion is we'll have to see, okay, this, I don't really like this problem that much, because what's going to create the free oxalate? What's going to create the free oxalate is this, water. Here. Water is going to pluck the proton off here to form hydronium and hydrogen oxide. Here, this would be step one of oxalic acid. And so what we're going to have here is 0.083296 molar, 0 and 0. And then the change will be minus x plus x plus x. And so at equilibrium, I'm going to have 0.083296 minus x, x, and x molar.
Okay, so I don't know if anybody else gets this, but how did you know to start? How did you know that that would be your step one? From everything else that we've done?
Because whenever they ask you a question like this, determine will it precipitate or won't it precipitate, and then we'll need to know what the concentrations are to determine that. And so this would be QSP here. The problem is we're given the concentration of calcium, but we aren't given the concentration of oxalate.
Okay.
And we might think that we could just plug this concentration in, the concentration that we calculated here. In here, but they're different species. So, for example, this is the concentration of oxalic acid. Well, one, it's an acid. This is the concentration of oxalate, which is a dibasic base. So they're different species. And so what we have to do is we have to figure out, well, oxalate. And this goes back to chapter 16. Well, if I do this as step one, I have hydrogen oxalate ion. But I know hydrogen oxalate ion itself is an acid. So in step two, I take my hydrogen oxalate ion and then hydrolyze water one more time. When I hydrolyze water one more time, I'll form hydronium and oxalate. And so this is the free oxalate concentration I have here. The free oxalate is what I need for this, right? Not the oxalate that's been bound to a hydrogen or two hydrogens here. And so what I'm doing here is step one, I figure out how much hydrogen oxalate. Step two, I take that hydrogen oxalate and figure out how much free oxalate I have. And so this is dichroic acid. And then once I get this equilibrium here, which is going to be very small, is it enough to cause precipitation here?
Oh, then you plug in the QSP and compare it to.
Yeah, then I plug it in here and then calculate Q. And is it big enough or not big enough?
Okay, see, that's where I was lost at, because when I did this at home, I just took the molarity and I plugged in there, and I was like, okay, well, this kind of makes sense. Because it was nothing near how you did on the video, so I was trying to find that correlation, but that makes sense now.
Okay, yeah, this is a complicated chapter because it's easy to get mixed up, as far as do you combine the equilibria or do you do it separately?
Yeah, that was going to be my next question.
Yeah, or do you calculate the solubility or you don't calculate the solubility?
Mm-hmm.
And so there are, for example, when there's a fractional precipitation problem, I always have like 10% of the students trying to do it by calculating the solubility and get stuck and end up not getting anywhere. They just stop at calculating solubility, but that, for that particular problem, it's not what we want. We don't want the solubility. The solubility is going to complicate things, but for other problems, that's what we need. And so it's just trying to recognize when you need it and when you don't need it. And probably the best thing for that is to look at a lot of example problems like this. So if we looked at something like,
So if the QSP is greater than the PASP, that means that there's more concentration of C2H4.
right, too much.
Does that mean that there is more precipitation?
Yeah, it'll precipitate. That is, this will precipitate. We don't want it to precipitate, and so what we can do is we can do another calculation. What is the max we could have here before precipitation occurs? That would be the constant. And then if that's the case, then I can make this problem a lot harder, because what I can say is, this is the max, okay? So what is the max I can have here? And then I can ask you, well, what concentration of oxalic acid is the max? What is the maximum amount of oxalic acid that I can add before it starts to precipitate? And then it becomes a harder problem, because if I'm asking you that, well, then I could make it even harder by adding solution dilution to that. If I add solution dilution, then that means additional steps. And so the other types of questions is, okay, what's the max of this? Then I have to work backwards here. In order to get this max, what would my initial have been here? And so this would be my unknown, and this would be my known, and then I work the table backwards. We did this before in other problems. We'll work the table backwards to figure out what the initial concentration must have been.
So if you want to find the max, do you just set it equal to KSP?
Yeah.
Okay.
Right, we set this equal to KSP and then you can calculate it. Here, we don't set it equal to KSP, because what we're going to do is we're going to figure out what the oxalate concentration is here, plug it in here, and then calculate the QSP and see if the QSP exceeds the KSP. If it does, then we get precipitation. And so, this problem, yeah. So this problem is a QSP type problem. In a QSP type problem, we keep things separate. And so let's see if there are other QSP type problems here that we can look at. Here. Let's see what kinds of variations in QSP they have. So in this 34, 100 milliliters of a clear saturated solution of silver sulfate is added to 250 milliliters of a clear saturated solution of lead 2 chromate. Will any precipitate form? All right, so this is going to be a QSP problem. And the precipitate that we're looking at is silver chromate here. So for silver chromate, we figure out silver sulfate won't precipitate because it's already saturated. And now we're adding more water. It's not going to precipitate. So silver chromate, what we have to do is we have to figure out the initial concentration of silver and the initial concentration of chromate, and then see if it exceeds KSP. So this is a QSP versus KSP problem, but this is a lot easier than 33. That's your solution blue.
Are there other like keywords that you look for when it comes to the other types of like problems? Like I know we have the KSPF and stuff like that. Like,
Yeah, there's a key thing, and that is in these particular ones, but it's a bit more complicated, because especially with KSPA, because the cadmium hydroxide, there's hydroxide directly in there. So if there's hydroxide directly in there, then we can get the POH directly. And so we don't have to do the combined method. One thing we could have done is, they were asking us what's the maximum pH. They should ask what the maximum pH is. If they're asking about pH, then that might have triggered you to think in terms of KSPA. And so we might have done this. We might have done that the cadmium hydroxide solid goes to cadmium 2 plus 2 hydroxides. And then we want KSP plus acid because we're asking pH. So automatically we might have done this. We might have said, okay, acid likes hydroxide. So we need 2 hydroniums plus 2 hydroxides. That's going to yield 4 waters. And this will be 1 over KW. And since we're doing 2 KWs, it's going to be 1 over KW squared.
And that would be the combined.
And this would be the combined method, KSP, and then combine these two. Not to say it wouldn't necessarily work. So for example, we'll have cadmium hydroxide here, it's called, plus 2 hydroniums. The cadmium 2 plus 4 water. This would be KSPA. Right, we could do an ice table with this. And then we could also figure out this. They didn't want it to. They said, what is the maximum pH that we can sustain this concentration of cadmium? So we're going to have a cadmium 2 plus concentration that we want to sustain. What was that cadmium 2 plus concentration? We didn't want it to precipitate, right? And so what we could do is we could figure out the hydronium ion concentration required. This is unknown. To leave the cadmium concentration, this at equilibrium. And so we could have done KSPA here, but it becomes more conceptually more difficult to see, what's happening. Because what problem was that? The cadmium one? Here it is. So we want it to stay at 0.0055 molar. And the situation is the more hydronium, the more this shifts to the right. And so the lower the pH, the more this shifts, increase the solubility. The less hydronium, the more this shifts to the left, because hydronium is a reactant here. So we figure out what is the maximum amount of hydronium that can sustain this, or the minimum amount of hydronium, whatever way you want to phrase this, that can sustain this. And so this would be KSPA, but for some problems, it's just easier to do it separate. For other problems, we have to do it combined. Now, if you're getting stuck on the test, then you want to try it both ways. First, you try it separate and see if you can do it. You might have to do it simultaneous. But if separate's not giving you the answer, then try to do it combined and see if that works. Because that will be actual. In this one, how could we do it separate or how could we do it combined? Because we're dealing with oxalic acid here. And it's not something that's going to be easy. So if we did KSPA, we could try it here. So automatically I might have thought KSPA. Well, if I'm thinking KSPA, then I think, okay, hydronium likes oxalate. This is going to produce hydrogen oxalate and water. When I look at this here, I say, okay, this reverse is Ka for hydrogen oxalate. And so since I reversed it, I'll flip it over to K like that. But then monohydrogen oxalate or hydrogen oxalate is also a base, and hydronium likes that. And so hydronium can react with this product that we just generated here. And this is going to form oxalic acid and water. And this is 1 over Ka for oxalic acid. And then we combine this here. This would be KSPA here. But this one is different. Because in this problem, they're not asking you what pH. You know, pH is the power of the hydronium concentration, power of hydrogen concentration. Or what POH, or what hydronium, or what hydroxide concentration will do this. And this one, it was just, you know, will it precipitate, which is a QSP problem. And so if I'm getting some question, where will it precipitate, I'm just going to set it up as a QSP, and I'm going to do it separate to figure out what the concentrations are initially. If I'm given a question of what is the pH or something, then it's giving you a clue. It should be a KSPA, combined method. This combined equation is not necessarily good either, because the combined method means the intermediate species here should be negligible in terms of concentration. That might be the case for this, but I think, there's a significant amount of monohydrogen or hydrogen oxalate, which we call monohydrogen. Hydrogen oxalate.
So when it's asking for the minimum or the maximum pH, then it's KSPA.
Yeah, but if you have hydroxide present in there directly, then we don't have to do it. We can do it separate based on POH. And so this one I would not do combined, because this has hydroxide, and POH and pH are so easily related. I just leave it in terms of hydroxide. I wouldn't convert it in terms of hydronium. And so I just leave this as is. The same thing with this. $30. What is the minimum pH at which, okay, this is hydroxide? And they should say, what is the maximum pH? Because higher pHs will precipitate, lower pHs don't precipitate. So they should be maximum pH. Okay, 31. Will the precipitation occur in the following cases? This is what I do in the homework, by the way. And it depends on how much time you have. Sometimes you're pressed for time, so you can only look at the homework once. Well, that's helpful for sure. But if you have more time, what you do is you go back through the homeworks and you analyze each homework problem. And then you put them into groups, and categorize them. And so this group of homework problems involve this type of technique in that group. And so once you have these cataloged in your mind, then for this type of problem, I should solve it this way. And that type of problem, I should solve it that way. Once we can categorize this into groups. And this is why I always got the complete solutions manual. I think the complete solutions manual is available for this book online. And then I just go through that with this and do it that way. I found that more effective to just look at the answers and then analyze them rather than trying to solve them, from the start. That's what I found more effective, because the reason I found that more effective was because the challenge problems on tests were always harder than the homework, is what I typically found the challenge problems to be. So I wanted to try to prepare for the challenge problems as best we could. So anyway, here, will precipitation occur in the following cases? So it's not dealing with pHs. This is just QSP, so we just compare QSP versus KSP. Okay, so this is just straight QSP, KSP, because there's no solution dilution here, and we just figure out the molarity and the molarity. Okay, then the next level problem is where we have to do solution dilution, and that was given by this, here. When one drop is added to this, that's solution dilution. So that's the next level of QSP versus KSP, solution dilution. And okay, it makes it a little bit more harder, having to do solution dilution first. then we come over here, the electrolysis. Okay, this is actually the next level. Let's see. Electrolysis can be represented. Electrolysis is 315 milliliter sample of 0.185. I didn't assign this problem because it's going to use too much other stuff going on here. But 315.185 molars continued until 0.652 liters of hydrogen at 22 degrees C and 752 milliliters of magnesium hydroxide precipitate. Well, this is a QSP versus KSP, except rather than doing a simple molarity comparison, rather than doing a solution dilution and then a molarity comparison, we have to do a Chem 1A style calculation, stoichiometry calculation to get the concentration and then do concentration comparison. So this would be the next level beyond that here where, okay, will magnesium hydroxide precipitate? So we need to know the magnesium 2 concentration, but in order to get the magnesium 2 concentration, we have to do some stoichiometry to get it. And then we'll get it. And notice that the magnesium 2 concentration remains constant throughout the electrolysis, but hydroxide increases. So the magnesium 2 concentration is constant, but the hydroxide's concentration increases. So we've got to figure out what the hydroxide concentration is in this case, and then determine will it precipitate. And we get the hydroxide concentration from stoichiometry. So that would be like another level here. Well, this is another level here, except we're not doing a chemical reaction. We need the oxalate concentration in this particular case. And in order to do the oxalate concentration, we have to go back to chapter 16. And we have to go back to chapter 16 to figure out how much oxalate results from this, which is a diprotic acid, and oxalates formed in the second step. And so here I'm just trying to figure out how much oxalates formed so I can plug it back into QSP, so I can see if QSP is greater than KSP and it precipitates. So all these problems are the same to me. All these problems are the same. They're just a QSP versus KSP, except they just try to make it more difficult to figure out what the concentrations are. Does that make sense, basically? And so all these for me are the same setup, except they have some other step involved to try to figure out what the concentration is. And so I'm going to go on to here, this next problem. And so 33 was tough because of chapter 16, and then it's a diprotic acid. And then it also is tough because we're just saying that the only thing that can pluck the hydrogen off is water, but what can also happen is the calcium can knock off the hydrogens to result in precipitation as well. That's okay. Let's look at number 34. Number 34 is a 100 milliliter clear saturated solution of silver sulfate. Now, clear saturated solution means that this is a solubility calculation. In order to get the silver ion concentration, I have to calculate the solubility because saturated solution solubility. And so this is more, because first I got to get the KSP for this and then figure out what is the splitting. Well, this splits into 2S plus S, which is going to give me 4S cubed, which is going to give me a solubility. But that solubility is not the silver ion concentration. Then I have to look at that original ice table and then triple it. Or double it because the silver ion concentration is 2S, not S. And so I get my 2S, and that gives me my silver ion concentration. And then on top of that, I have to do a solution dilution. Then after I do the solution dilution, then finally I have my initial silver ion concentration that I can use for a QSP calculation.
Can we do this one?
What's that?
Can we do this one?
Yeah, we can do this one. So we already know I already know what's going to precipitate because the silver sulfate is not going to precipitate. It hasn't precipitated. And if I add more water, it's still not going to precipitate. What I'm worried about precipitating is silver chromate. And so this is a QSP problem because I'm asking the question, will silver chromate precipitate? So in order to determine if silver chromate precipitates, then I need to know the initial concentration of silver and the initial concentration of chromate so that I can calculate QSP and then compare it to KSP. If QSP is greater than KSP, I get precipitation. If it's equal, then it's saturated, or if it's less than, I get no precipitation. Actually, if it's equal or less than, I get no precipitation. If it's greater than, I get precipitation. So in order to calculate QSP, I need to know what the silver ion concentration is and what the chromium ion concentration is. The chromium ion concentration is a straight solution. Oh, no, it's not a straight solution. You know, they're making a lot of busy work for us for this particular problem because they aren't telling us what the concentrations are. If it were a straight solution, it'd be a lot easier. But they're going to make us. And so I have 100 milliliters of saturated silver sulfate. And so what I need to know is what is the silver concentration in saturated silver sulfate? Well, in order to get that, I have to do another QSP. And so here I have to do the silver sulfate solid goes to 2 silver ions plus the sulfate. And I'll need the KSP for this since it's saturated. So if it's saturated, then what that means is if I take some silver sulfate, I'll saturate it. That means I'll start off with 0 here. The change will be plus 2S plus S, and I'll get 2S and S molar. And then I'll solve for this. This is going to be 4S cubed, which means S is going to be KSP divided by 4 cube root. But once I calculate what S is, then I'll have to plug it back in here and multiply it by 2 to get 2S, which is the silver ion concentration. And so the silver ion concentration here is 2S. And so I need the silver sulfate, the KSP for that. One point 4 times 10 minus 5. So what does it come out to?
0.01518.
0.051518?
0.01518.
1518. Okay. 0.1518 molar. And then what's the concentration of silver ion?
0.030365.
Okay. And so here, the silver ion concentration, we end up with having to do this to get it 0.03036. You know that? Okay, plus to this, we're going to add another solution with the lead or the chromate. What was it? Let's see. Lead chromate, saturated solution of lead chromate. And so this is going to be 250 milliliters of saturated lead chromate. So we'll have to do KSP equation here. Lead to chromate solid goes to Pb2 plus chromate. And so in this case, it's 0, 0, plus S, so we get S and S. So KSP is equal to S squared, and S is just equal to the square root of KSP. So we'll get the KSP value for lead 2 chromate. It's 2.8 times 10 minus 13. So this equals the square root of 2.8 times 10 minus 15, which gives us an S of what?
5.291 times 10 to the negative 7.
Which is equal to the chromate concentration. So the chromate concentration here is 5. What was it again?
291 times 10 to the negative 7.
Okay, then we'll do the solution dilution here. When we do the solution dilution, we're going to end up with 350 milliliters total. And so we'll figure out the new silver ion concentration. The new silver ion concentration is a 100 to 350 dilution of 0.03036 molar. So go ahead and calculate that and see. And the same thing we do for the chromate concentration, which is going to be a 250 to 350 dilution. 250 to 350 dilution of the 5.291 times 10 to the minus concentration. And then we plug that into the QSP equation and see, does it exceed KSP or what? The QSP equation is going to be equal to the initial silver ion concentration squared. The initial would be after solution dilution times the chromate concentration. And then compare it. Does that kind of answer it or enough, or do you want to finish it? I'll finish it. So what did you get for the silver, the diluted silver ion concentration here?
0.0086757.
Okay, and then the chromate concentration?
3.7796 times 10 to the negative 7.
Okay, then we'll plug it in here. The square root of that. The silver.
.52677 times 10 to the negative 5.
Okay, then we'll compare it to the KSP of silver. That's, did you multiply the chromate?
Oh, no, I didn't.
Okay, multiply the chromate. Which would be 5.291.
Why wouldn't it be the 3.77?
Oh, 3.77, so. 3.7796.
2.8448 times 10 to the negative 11.
All right, so about 2.8 times 10 to the negative 11. And then let's compare it to silver chromate, which is 1.1 times 10 to the negative 12. So we got 2.4 times 10 to the negative 11. 2.4 times 10 to the negative 11 is bigger than 1.1 times 10 to the negative 12, which means we're going to get a precipitate. So precipitate forms. But QSP is bigger than KSP.
So which one are we looking at again? Was it silver chromate?
Yeah, silver chromate. 1.1 times 10 to the negative 12. Now, this is a tough chapter because there are a lot more ways we can do the problem. But in this block of homework problems, they're all the same. They're QSP versus KSP problems with just additional work on trying to figure out what the concentrations are. And, we'll do it separate here. Versus something like solubility and pH. What types of solubility and pH type problems do we have? Some of these are just qualitative, in Le Chatelier's principle. So qualitative Le Chatelier, we don't have to really do anything. We don't have to do combined. We just look. Like KCl, solid, goes to potassium ions and chloride ions. Potassium ions are neutral, chloride ions are neutral, so that's nothing there. But magnesium carbonate goes to magnesium ions and carbonate. Carbonate's a base, a dibasic base. And so that's going to, we can use Le Chatelier's principle. That is, if we make the solution more basic, then it shifts it to the left. If we make the solution more acidic, then it shifts it to the right. And so we look at what reacts. Carbonate reacts with acids. That's why we make it more acidic, it shifts to the right. This is also qualitative. Here's a calculation, but it's hydroxide. Hydroxide's POH. So we don't have to do KSPA here. We just look at the hydroxide concentration, relate that to the POH, and then relate it to the pH, like we did for the cadmium. The other ones, this is very similar. Except this one is, what is the solubility of magnesium hydroxide in a particular buffer solution? There's points. The solubility is 0.65 grams. What must be the pH of the buffer solution? And so this tells us the solubility, which is the equilibrium. The solubility of this is equal to the concentration of magnesium because it's 1 to 1. For every one of these, we get 1 magnesium. But it's not equal to the hydroxide. The hydroxide concentration is double the solubility. And so it would be 0.65 grams per liter of this compound. And so that's 0.65 grams. We convert that into moles. We get moles per liter. And then we figure out this is going to be the same number of moles of magnesium. And therefore, we can figure out what the hydroxide must be here in this case. But we don't have to have a separate equation. We don't have to have, let's say, a buffer combined with this or whatever else. We're just figuring out what the hydroxide is, and that gives us a POH, which will give us our pH. Does that make sense here? Now, this is the same thing. Here, this is magnesium hydroxide. And what we want to do is we want to prevent precipitation. So we have a certain amount of magnesium, 0.100. And we got to figure out what the max hydroxide is. And so the max hydroxide is going to be the POH min, which is going to be the pH max. Once we figure out the pH max, then this is a buffer solution. This is the Henderson-Hasselbalch buffer. And so we just set the pH here in the HH buffer. And so this is not a KSPA either. This is just hydroxide, but in this case, we're using a buffer to get that hydroxide. This is kind of the same thing. This is aluminum hydroxide. And so here, this is just a straight hydroxide, you know, if we have this much aluminum, how much hydroxide? And how much hydroxide is POH? And then we can figure out pH. So what is the maximum pH at which this will precipitate? I don't know why they're saying minimum pH. Well, I guess the minimum pH would be the lowest pH, which it will start to precipitate. And so I think of it in different terms. I think of it as not having precipitated yet, and then raising the pH, which raises the hydroxide and eventually it precipitates. They're thinking maybe from a dissolution perspective. At high pHs, it's precipitated. So if we drop it, then it'll dissolve. At what pH will it dissolve? That's what they're thinking. But here, this is hydroxide, so we don't have to worry about it. In fact, all these are hydroxides here. So none of these require KSPA equation.
A quick question. This was the example that we just did on the board. So if we were to look at this like in like a stepwise fashion, so the finding the concentration for the silver would be like the first step, and then the second step would be finding the concentration for the chromate, and then the third step would have to be the solution dilution of both. And then the fourth step would just be finding QSP and then juxtaposing it with the KSP.
That would be it. But sometimes finding the concentrations are easy because they give you the concentrations. Is what I was saying earlier. This is criteria for precipitation. So sometimes they just give you the concentrations and you just figure it out. Sometimes they make you work to get the concentrations and then figure it out. Then we have completeness of precipitation. You know, completeness of precipitation, typically we do solution dilution and then do ice table and figure out, you know, how much, what is percent remaining in the solution after the ice table. Now, fractional precipitation, we don't calculate the solubilities, we don't calculate the Q, even though you think we should calculate the Q, and you think we should calculate the solubility. For fractional precipitation, we calculate the concentration of the precipitating agent required for precipitation. And so I'd look at all these and see what kinds of variations they have for fractional. And I'd look at these and see what kinds of variations they have in this. And so here, 200 milliliters of potassium chromate, 200 milliliters of silver nitrate. So we're looking at silver chromate precipitation here. So the first step is solution dilution. Once I do the solution dilution, then QSP must be greater than KSP because we're going to precipitate. And so we're going to set up the ice table and do the ice table calculations here. We aren't actually going to calculate QSP because they're asking us what is the percent left unprecipitated. So we're going to assume that QSP is greater. And so we're going to go one step farther with this. Like here in the previous group of questions, we're just asked, is QSP greater than, less than, or equal to? In this one series, QSP is greater than, we're going to get a precipitation, how much precipitation. And so I'm going to skip the QSP calculation because it's not necessary to do QSP calculation. Here I already know what's going to happen. Although I could do QSP calculation, and I could see that QSP is going to be greater than KSP. It would be a waste of time. Same thing here. QSP is going to be greater than, I'm going to skip that calculation and just figure out how much precipitates, how much remains. Here, constant chloride. Constant chloride means it doesn't change initial to final. What percentage of lead will remain in solution after PbCl2 precipitates? What chloride should be maintained to ensure only 1%? And so this is the one, actually somebody asked me, 99%. So if I only want 1% of the lead to remain, can I do that? Now this is an extra twist. The other ones, I just go ahead and let it naturally react and then figure out how much is left over based on what the initials are. This one's an extra twist to that. And the extra twist to that is this. I'm going to try to control how much precipitates, and not be subject to it. Like, for example, this one might be like 5% remains, or 0.5 or 0.005% remains. Whatever we get is what we get. In this one, we're adding an extra twist to it where we're going to try to control exactly how much reaction occurs. There are different ways we can control how much reaction occurs. I'll probably cover this tomorrow morning too. But in this case, we set up the ice table a bit differently than the others. In these ones, we just set up the ice table as normal, 35. Something like that. We're looking at the precipitation of silver chromate. And whatever the initial is here, we'll just let it, go until we get to the equilibrium. For these, we automatically reset because KSP is very small. KSP is very small, it's mainly reactant, so we always reset these here. And then we figure out what the equilibrium concentrations are here. Yeah. 37 is different. In problem 37, we're trying to control how much precipitates. And so we only want 1% to remain. But in order to do that, we can't make the problem too hard. So this is PbCl2. Okay. What chloride should be maintained to ensure? And so in the first problem, we can call it 37A, we just let it happen naturally and then see how much it precipitates. So here, the ice table is set up a little differently. This is 0.065 molar to begin with. And this is 0.100 molar. But the 1.100 molar stays 0.100 molar all the way to equilibrium because they say it's constant. And so what we do is we figure out, well, how much lead can we maintain with an equilibrium amount of chloride? Here. And so this is going to be 0.065 minus X. So this is 2 chlorides here. And so it gets a little complicated because, okay, this is the maximum amount of lead I can have at this concentration of chloride. So this is kind of like fractional precipitation type calculation, in which we're going to calculate this lead at the end of precipitation. This is where we're going to stop the precipitation. We're going to stop the precipitation when we have 0.100 molar chloride. And then we calculate how much lead remains in solution. And so the amount of lead remaining in solution is just going to be KSP divided by the chloride concentration squared. And so this is the amount of lead remaining, and then we calculate the percent precipitation by comparing it to how much we had there originally. Does that make sense? Yes. Okay. In the part B of this one is this whole new problem. So this is part A. In part B, we're given the lead and we're going to calculate how much chloride. But they're making us work for how much lead there is. Because in part B, we're going to start off with the same amount of lead. And so part B is, we start off with the same amount of lead here. We're going to be Pb2 plus 2 chloride. We start off with the same amount of lead here, 0.065 molar, but we want only 1% of that to remain. So 1% is 1 out of 100, which is 1 over 10 minus 2. And so if I only want 1% of this to remain, it's going to be 0.006, 0.01 times this is 2. This minus 2 is 10 minus 4. Is that right? Can't do math. So 1.01 times 0.065. Yeah, so that's right. And so in other words, this is 1% remains. That means 99% must have precipitated. Does that make sense? And therefore, what must the chloride be in order to sustain this as saturated? And so how much chloride must I have here? And so I just solve it for chloride. So again, these are calculations that are similar to what we did when we stopped at fractional precipitation. How much remains, and so this is the same type of calculation as that. This completeness of precipitation. And then we look at the fractional precipitations. All these fractional precipitations are similar. And so what we're trying to do when I go through this is I'm trying to catalog different setups because there are a lot more different setups in this chapter than in, let's say, the previous chapter. And so that makes it more complicated. Yeah, that's why you get lost, because you might try a setup that, it's not necessarily harmful. You can do any setup you want, but if you get stuck, then don't dwell on that setup. Try a different setup. Try to calculate a different thing. So this is why, if you get stuck on something, you should try different things and then maybe make that connection. This type of stuff you want to do early, because if you can make those connections early, then you have the neurons all connected, the branches. The thing that's tough is when it clicks, after the test. Okay, then, I should have used this setup, but it's too late now because the test is already over. So we try to get it done before, but it's hard because there are a lot of different setups here. But tomorrow we can look at some more. I'll probably do this sometime.